We will now start our first topic for general mathematics, which is on functions and relations. Our first subtopic is on basic concepts of functions. Now let's have first these three important definitions. Now, what is a relation? A relation is any set of ordered pairs. When we say ordered pairs, the elements must be like this: x, y. Now we have the first component and the second component y. So for example, we have this set, the set containing ordered pairs 110, 220, 330, 440, and 550. You can make your own relation by giving any set of ordered pairs. Say for example, 1, 3, negative 5, 4, negative 1, 0, close. This is a relation because the elements of this set are ordered pairs. So this is an example of a relation. So again, a relation is any set of ordered pairs. Next, we have the domain. The set of all first components of the ordered pairs is called the domain of the relation. So going back to our first example, this same set, the first components of the ordered pairs are 1, 2, 3, 4, and 5. Okay, so our answer will be, we can write D for the domain of this relation. Okay, for example, R is the set containing 1, 2, 3, 4, and 5. Notice that we only list down the first components of every ordered pair. So the elements of the domain are not ordered pairs, but mainly an element or elements, which are the first component of the ordered pairs. Okay. Now take note that when we say set, the elements must be distinct. Now, for example, I have this relation 1, 2, 2, 3, 1, 4, 3, 5. Now, what is our domain for this relation? The domain is the set containing 1, this 1, 2. There's another one, but we already wrote 1. So, do not write 1 again. Okay, so proceed to the next ordered pair, 3. So we have 1, 2, and 3 as the domain of these relations. Now next, what is a range? The range is a set of all second components of the ordered pairs. Oh, so this is typo. So this is range, not the domain. Okay. Now let's consider the previous example. What are the second components? We have 10, 20, 30, 40, and 50. So the range of the given relation contains 10, 20, 30, 40, and 50. Okay, so that is the range. So the domain is your first component, the range is a set of your second components. Now let's go to function. What is a function? A function is a relation in which no two ordered pairs have the same first component. Okay, so for every ordered pairs, no two of them must have the same first component in order for it to become a function. Now we can use a mapping diagram to know if a relation is a function or not. So our only concern here is the first component. It should be one component, one domain maps to one range. First component. Okay, tell whether the following are functions f or not f. For example, number 1. Is this a function? Look at the first component. We have 1, 2, 5, and 6. Okay, looking at the mapping diagram, this is the mapping diagram. No two ordered pairs have the same first component. So number 1 is a function. No two ordered pairs have the same first component. Okay, look at that. 1 is only mapped to 3, 2 is only mapped to 4, 5 is only mapped to 7, and 6 is only mapped to 8. Now how about example number 2? Okay, let's check the mapping diagram. Look at that. Look at negative 2. Negative 2 is mapped to 4 and negative 2. This one, these two. Okay, so meaning we have a domain or a first component which is negative 2 that is mapped to two different second component which are 4 and negative 2. So meaning it does not satisfy the definition of being a function, because a function must have, or no two ordered pairs must have the same first components. So since we have two ordered pairs, no, this one and this one are the two ordered pairs that have two first components. Therefore this is not a function. It does not satisfy the definition. Number 3, again, look at that. We have negative 1, negative 10, negative 1, 15. So we have negative 1, the same first component. So two ordered pairs with the same first component. So this is not a function. And last, look at that. So no two ordered pairs have the same first component. So this is our last function for this example. So only 1 and 4 are functions or examples of functions. Now, function as notation. Functions are usually expressed in equation form. Okay, think of a function as a machine which is programmed with a rule that defines the relationship between the input and the output. So we have the input and the output. Consequently, the machine accepts the member of the domain, which is the input, okay, and releases the member of the range, which is the output. So we have the notation f of x or f at x. Our f is our function, x will be our input, or x is in our domain, and f of x our output. So f of x will be in our range. So that is, we have an ordered pair, input, output. So we have this x fx or xy, because we usually equate f of x as y. So going back to our motivation, the ATM. So when we go to the ATM to get our money, of course, we have our ATM card, of course, right? So upon or after inserting your ATM card, what will you put, or what will be your input next? It will be your PIN. So this will be our part of the domain, and the money will be, of course, our output. So we can have this in symbol F of our input PIN, and our output will be our money. Now functions as a graph in the Cartesian plane. Now how can we know that a graph is a graph of a function? No, so meaning when we look at a graph, can you tell directly that it is a function or a graph of a function? Yes, by the use of the vertical line test. What is a vertical line test? It is a graph represents a function if and only if each vertical line intersects the graph at most once. Okay, so literal vertical, like this. Just create a vertical line, and if it intersects the graph at most once anywhere sa graph, then the graph is a function, graph of a function. For example, which of the following graphs can be graphs of functions? Now examine letter A. Now notice that anywhere I put a vertical line, it only hit the graph only once, at most once, okay, at that point. So letter A is a function of a graph. Okay, how about letter B? Okay, we have this point once only, so this is also a function of a graph. This is a function, graph of a function. This one, okay, also once, so this is also a graph of a function. Now how about D? If I draw a vertical line, look at this, I hit 2 points on this figure, on this graph. So take note, in vertical line test, it must hit at most once, meaning the maximum number of points intersecting the graph with a vertical line is only 1. So since there are 2 points, so this is not a function. How about E? Okay, so we have this, so this is not a function. Now these are, so only two, D and E are not functions, graphs of functions, because they do not satisfy the vertical line test. Now which of the following represents functions? So if you notice, 1 2 3 4 5 are in equation form. So we have read this note. The x variable is the input, as what I've said, diba, f of x. So x is our input, and that the value of the y variable is computed based on the x variable. Take note, we have f of x equals y. We have this now. So our y depends on our x. So our relation is a function if for each x value there corresponds only to one value. So your x here must correspond to only one y value. So for these 5 examples, all are functions except for number 3. Okay, why? Because if you substitute x equals 0, take note, x squared plus y squared equals 1. If x is 0, then we have y squared equals 1. So take the square root. Taking the square root both sides of the equation, we have plus and minus 1. Take note, we have f of 0 will be mapped to 1. F of 0 is also mapped to -1. Take note, there must only be one y value. So since there are two y value for number 3, two y values for number 3, 1 and -1, so number 3 is not a function. The rest, 1, 2, 4, and 5 are functions. Meaning, if you substitute a value of your x, we can only get a single value of y. Only one value of y. Last, so the domain of a relation, therefore, is the set of all possible values that x can take. Now, take note, we have f of x. So x is in our domain. So recalling our previous example from the previous slide, the domains of these 5 are this. We say that the domain is all the set of real numbers for number 1 if you can substitute any values of the set of real numbers to your given equation. Now we have a result that if your function is a polynomial, just like number 1 and 2, no, just like this 2, then the domain of this polynomial is always the set of real numbers. Okay, now for number 3, let's just go back to number 3. Let's start with number 4. For number 4, take note that when we talk about square root, when we talk about square root, say for example square root of a must be greater than or equal to 0. Okay, because the largest set here that we're talking about or using is only the set of real numbers. We will not go to the set of the complex numbers. Okay, so a is greater than or equal to 0. So meaning, from number 4, square root of x plus 1. So meaning, in order for this to be defined, x plus 1 must be greater than or equal to 0. So solving for x greater than or equal to -1. So meaning, writing this in notation form, so we'll start with -1 to positive infinity. Okay, that is for number 4. Now for number 5, we will tackle this in another topic, and more on another topic. So number 5, take note that it is a rational or in fraction form. Now take note that a fraction is undefined if your denominator is 0. If your denominator is 0, then it is undefined. So meaning, if x minus 1 is 0, the denominator, which is solving for x, we have x equals 1. So meaning, if x is 1, your denominator is 0. So we cannot let that happen. So that is why we will delete that from the set of real numbers. So the set of real numbers except 1 is our domain. So in interval form, we have from -infinity to 1. So parenthesis, we cannot use bracket because 1 is not included. Union 1 to positive infinity.